Have you ever noticed how scientists can be, well, a little obsessive about the way they write down numbers? It's not just about being tidy, it's really about precision and honesty. Today, we're going to decode the secret language they use, significant figures. It's how they tell us what they actually know and what they're just guessing at.
Okay, let's jump right in. Look at these two numbers on your screen, 250 and 2.50. Now, mathematically, sure, they look like the same value, but to a scientist, one of them is basically screaming with confidence, while the other is kind of shrugging its shoulders. Which one is which? Stick with me, because by the end of this, you'll know exactly why one is so much more powerful than the other.
So why all the fuss? Well, in science, if you can't trust the numbers, you can't trust anything that comes from them. Significant figures, they're like a built-in reliability rating for any measurement. They let us communicate just how good our data is, so we're not claiming a level of accuracy our tools just don't have.
So what's the official definition? Think about it like this. Imagine you're measuring something with a ruler. You can see the certain digits really clearly, right? But then there's always that last little bit where you have to kind of squint and guess between the lines. Significant figures are all of those digits put together, the ones you're absolutely sure of, plus that one final educated guess. That's the secret sauce.
And this is where it all starts to click. Let's say you measure something with a standard school ruler. You might get 2.0 centimeters. Okay, fine. But what if you use a super fancy pair of digital calipers? Now you might get 2.000 centimeters. Those extra zeros aren't just there to look pretty, they're a direct message telling you, hey, I used a really precise tool for this. More sig figs always means more precision.
All right, so how do we actually spot these significant digits out in the wild? Well, there's a simple set of rules. Think of it as your toolkit. Once you get these down, you'll be able to look at any number and instantly understand the story it's trying to tell you.
It really all boils down to these 4 core rules you see here. Most of it is pretty straightforward, but the real trick, as you'll see, is figuring out what to do with all those zeros. So let's break them down, one by one.
Okay, rule number 1. This one's the freebie, the easy one. Any digit that isn't a zero, so 1 through 9, is always significant. Doesn't matter where it is. It counts. That's it. Simple as that.
So, if we see the number 345, well, there are no zeros to worry about at all. We've got a 3, a 4, and a 5. That means we have 3 meaningful digits, 3 significant figures. See? Easy. All right, on to our first rule about zeros. What happens when a zero is sandwiched right between 2 other significant digits? Well, you can think of those zeros as being captive. They're stuck, they're not going anywhere, so they have to be counted. They're always significant.
For example, take the number 1002. Those 2 zeros in the middle? They're trapped between the 1 and the 2, and since they're sandwiched, they count. So we count the 1, both zeros, and the 2. That gives us a grand total of 4 significant figures.
Okay, how about zeros at the very beginning of a number? We call these leading zeros, and you can think of them as, well, they're like stagehands in a play. Their only job is to hold the decimal point in the right spot so the important digits get the spotlight. They're just placeholders, so they are never ever significant. So if you see a number like 0.0045, you can just mentally, poof, ignore all those zeros at the start. All they're doing is telling you that this is a small number. The real action, the real measurement, is in that 4 and that 5. So that's just 2 significant figures. And here we go. This is the big one. This rule solves our whole mystery from the beginning. It's all about zeros at the end of a number. And the hero of this rule is the decimal point. If you see a decimal point anywhere in the number, like in 2.50, it means that trailing zero was put there on purpose. It's showing you precision. It absolutely counts. But if there's no decimal, like in our number 250, we have to assume that 0 is just a placeholder. So 250 has 2 sig figs, but 2.50 has 3. And that, right there, is the huge difference.
Okay, so we know how to count them. That's step 1. But where does the rubber really meet the road? Let's get into the practical stuff. How these rules totally change the way you're supposed to do math. Now, the basic idea of rounding is probably familiar to you, but now we have to apply it with purpose. You figure out which digit is the last significant one you're allowed to keep. Then you just peek at the very next number to its right. If that neighbor is a 5 or bigger, you bump your last digit up by 1. If it's 4 or smaller, you just leave it be and drop everything else. Now, when you're actually doing calculations, there's a really important split.
For multiplying and dividing, it's all about the total number of significant figures. Your final answer can't be more precise than your least precise measurement, your weakest link. So you find the number with the fewest sig figs, and your answer gets that many. But for adding and subtracting, we totally ignore that, and instead, we look at the number of decimal places. Your answer is only as precise as your sloppiest measurement after the decimal point.
Okay, you've got the toolkit. You know the rules. It's time to put all this to the test. I'm going to throw a few numbers at you, quick fire style. Let's see what you've got. Ready?
First one up. How many significant figures are in the number 0.00340? Think about those zeros at the front and pay very close attention to that zero at the end.
And if you said 3, you nailed it. Awesome. The zeros at the front are just placeholders. They don't count. But that trailing 0 at the end comes after a decimal point, which means it's significant. So we've got the 3, the 4, and that final 0. 3 in total. Okay, next one. This time it's rounding. Let's take the number 4.567. What does that become if you're only allowed to keep 3 significant figures?
The answer is 4.57. Our 3 significant figures are the 4, the 5, and the 6. So we peek at the next number over, which is a 7. And since 7 is 5 or bigger, we've got to round that 6 up to a 7. Perfect.
All right, final question of the challenge. Look closely at all 4 of these options. Only one of them has exactly 3 significant figures. Is it A, B, C, or D?
And the correct answer is C, 4.50. The 4 and the 5 are a given, and because of that all-important decimal point, that trailing 0 counts too, giving us 3. Remember, 450 without the decimal point would only have 2.
So after all these rules and challenges, let's circle back to the biggest question of all. Why bother? Why can't we just write down every single number our calculator spits out? Because doing that is, well, it's basically lying about your data. Your calculator has no idea what tool you used. By reporting too many digits, you're making a false promise about how precise you were. Significant figures aren't just some boring rule from a textbook. They are the honor code of science. They are how we stay truthful about what we really know and, just as importantly, what we don't.